So I'm here to introduce Yiming's presentation of Jaime Carbonell's work on XLNet. But before I do that, I want to say a little bit about Jaime's history as a sort of forefather of question answering research. XLNet is a very significant development in the application of deep learning techniques to question answering. And has achieved very high benchmarks on some very important QA data sets. And it represents essentially what many people consider, one of the state-of-the-art approaches in modern question answering. But in reality, question answering has existed long before the development of deep learning techniques. And Jaime Carbonell was actually there at the beginning. So the first system that we think about as a sort of modern computer science approach to QA came in the late 70s with the lunar system, which answered queries about moon rocks by crafting relational queries. Then when he was a young faculty member at CMU in the early 80s, Jaime had worked as a consultant for Digital Equipment Corporation. And he developed the first dialogue-based QA systems that could answer questions about computer equipment. And of course, being Jaime, he thought about having a system that could answer questions from anybody, whether it was the salesman or the technical person who had to requisition the equipment. So if you go back and read the paper that's cited here, you'll realize that he figured out how to solve problems like how big is this disk, was referring to the physical size of the disk drive or the storage capacity of the disk drive. So when I was in my 20s and beginning a career in question answering, Jaime's paper was one of the first papers that I read. Also in my first job out of college, I built probably at that time was the most sophisticated corporate QA system, which was used by GT Telephone as an interface to all of their billing databases. And that was the result of Jaime's consulting with my company. And that's how I met Jaime, and that's how I eventually came to Carnegie Mellon to do my PhD. Jaime was also a huge influence on getting QA established in the LTI as a major research area. He participated in a white paper that was written in 1999, which resulted in the government giving funding for something called the Acquaint program. And that funded research at LTI for 7 years and led to the creation of IBM Watson in a kind of indirect way. So you can see here all the faculty and all the graduate students that participated in this. And many of these folks have gone on to become successful researchers or faculty members in their own right. And this was the time when we started thinking about how to use statistical machine learning for question answering. And you can see Jaime there with his graduate students. So this was really when we started doing this. And if I think now to where we are today, there's just been tremendous strides in the application of deep learning to question answering. So, with a little bit of history, now I want to turn things over to Yiming, who's going to tell you about XLNet, which was Jaime's latest and greatest development in the area of automatic question answering.
So today I'm going to talk about the XLNet. XLNet is one of the last pieces we jointly work with Jaime. So this is primarily the two first authors is Zhilin Yang and Zihang Dai. And Zhilin was Russ' student, and Zihang Dai is jointly supervised by Jaime and me. And both are already graduated with excellent thesis. Zhilin was last year, Zihang is just this summer in August. So that's the very high quality work. So this is really not about the question answering, but more generically, it's a new way to learn representations of natural language in the unsupervised way. So this slide shows the trend in the past decades in language representation learning. The left portion are the word-to-vector mapping, or let's say word embedding, early work in word embedding. So that means they basically given a huge amount of unlabeled natural language data. You can learn a vector for each word. And then later, the research effort shifted to a new paradigm called context to vector mapping. So that means really this work includes transformer, ElMo, GPT, BERT, and XLNet, and more. And so those methods are really trying to learn that do a one-to-many mapping of each word under context in the testing case. Now, so let's consider a motivating example about the word bank. In the context of the river and in the context of a financial institution, if you use a fixed vector to represent the words in isolation of the context, it's clearly suboptimal. But if you can establish a learning mapping, depend on the different contexts and mapping them as words to different vectors, then that's more semantically more expressive. So that so then I will outline the two parts of work. The first part is just a quick review of conventional word embedding, and the second part is a contextualized representation learning. So for the first part, there's a bunch of different methods. I will use a CBOW and schemagram as an example. And for the second part, I will go through ElMo, BERT, and XLNet. So probably many of you are already familiar with this diagram. On the left half is the method called CBOW. On the right part half is the method called speakgram. So then in CBOW, the input is some context words. And basically it's a neural network parameterized by a matrix W and W prime, and they trained on the training pairs, and the pairs are word context pairs. In CBOW, the context is treated in the training process. It's on the input side, and the system will make a prediction about this, the words. The context is the central words or target words. The context is about, and on the skipgram is the opposite. The input is a particular word of interest, and the output is context, and they use this kind of larger amount of training pairs to train the model parameters. To be a little bit more precise, so the first thing is how do we get the training data? You just apply a sliding window over, say, a sliding window of size C. Size C means the window consists of C words. That you apply this sliding window about each words that over the unlabeled data set, natural language text, then you will get many of these context and word pairs. And the red here is the word of interest, and the left, right, 2 minus C words are together is considered consists of the window, a context window. And in CBOW, the objective function is to maximize the log likelihood over all the possible training pairs and the log likelihood of seeing the target words given its context. And skipgram is a little bit just the opposite, just swap the log probability part is predict the context given each word. And the context is further decomposed into individual words in that context. So the next, we just focus on these two methods are very symmetric and very similar, are developed at the same time, also both developed at Google. So we just focus on CBOW. So look at this concrete example in here. Suppose we'll have a sequence, and the red part is the sliding window, and the blue part is the central words or interesting, and the plus and the window and the plus and minus towards on the left and towards the right together is consists of the local window about that word. So again, so once you have so many of those word context pairs, so you can train this kind of neural network, where that so each word is in the training set is represented as a one-hot vector. That means the vector size is the length, is dimensionality is the vocabulary in the training set, training set collection, and all the elements are 0 except the ones corresponding to particular words will be 1. That's called a one-hat vector. And so once given the input, if you have some the model parameter W and W prime, basically W first of all convert each one-hot vector or lower dimensional vector in the hidden layer, and to they apply they do that for every contextual words and sum together on the hidden layer, and then they use another parameter matrix W prime to decode this hidden layer to again the high dimensional vector, which is the vocabulary size, that's called Y, vector Y. So that is the architecture of this this model. So that then they were trying to hope that during the training process, they were trying to make the system predicted Y is as close as possible of the one-hot vector of the target words. So here, then another thing is you notice that when from the input layer to the hidden layer, we're trying to do the operation is the matrix W, which is a parameter matrix, multiply a one-hat vector. So this operation really actually is determined. In fact, this operation is equivalent to pick the corresponding row vector in matrix W. So in that sense, because the design of this architecture is determined that the W, each row of W is actually the word embedding. And in the beginning, when you train the neural network, this word embedding may not be optimized, but when you train, then you do this forward and backward propagations. That's a typical neural network training process. And then this W and both W prime are iteratively optimized once they stabilizes, they end up with the optimized word embedding with this kind of training data. So that's pretty much, just to be more precise, we want to maximize the log likelihood over all the summation of all the training pairs and the log likelihood of the probability of generating the target words, target words given this context. And this probability is estimated using some softmax function, and which one of this inside the part of the function is the encoding of each word out of context, and also the context encoding of the contextual words. So that's to get a little bit more details. There's we can collapse the input layer about each word into a more compact notion here. So that here's the input. In fact, is just the average, essential context representation, which is just the average of all the context one hat vector of those context words, and then that's and the hidden layer just a linear transformation of the contextual word context vector, and then after that you follow another linear transformation for the decoder part, and there's the last layer. You can consider that two vectors in parallel. One is vector u, another is vector y, and the vector u is the again it's a v-dimensional vector that before the softmax normalization. The y is the normalized vector of u through the softmax operation. So I guess I can skip the. So the whole idea is that once you, the whole idea is the rest. A few slides just to say how this forward-backward propagation can be performed, and given there's a loss function. I will not focus on details, but just saying that you can start from any arbitrary setting of the two matrices, and then you use some gradient updates rules. And so that requires, in order to optimize those two matrices, you need to be able to derive the gradient of your objective function with respect to those model, each of those model parameters in these two matrices. So in order to do that, derive this gradient properly, you need to have the dependency graph that here's the input layer, here's the hidden layer, and here's the vector of u, and the last layer is the vector of y. And following this, you can write the correctly derive the gradient. And then once you have the updating rule, all you need to do is iterative updating of matrix W and W prime. So then I'll skip the details of how to derive that. This is actually a part of my lecture. So remarks. So the neural networks provide an efficient way through differentiable objective functions to learn word embedding automatically. However, using a fixed vector to represent each word cannot capture word meanings in dynamic context. So then the next that leads to the next generation of methods focus on contextualized representation learning. So now we enter the part 2. So existing approaches can be largely divided into three categories. Well, maybe 2 categories. one is called autoregressive methods. And among those methods, ElMo is a representative example. And another category is called autoencoding methods, among which BERT is a representative example. So both methods have their strengths and weaknesses. So then XLNet is a new approach, relatively new approach that combine the strengths of both and address their limitations of the two categories, AR and AE. So let's look at the AR category. So those methods is really based on, derived from standard language modeling. So we just have a quick overview of standard language modeling, which has been a dominating approach in both machine translation and information retrieval for the past 2 decades. So basically, they treat each sequence, data sequence X. So supposedly, we'll have a data sequence of t-dimensional length of t. Then we can derive the tokens as a x of 1, x of 2, x of t. And the boldface X is a vector or the sequence of X. The sequence can be, the probability of the sequence can be factorized using standard Markov chain. So that means this the joint probability of the entire sequence is the multiplication of each token give its context to the left. That's, so then using this, so that means if we can, the system can predict this kind of conditional probabilities, then we can use many training data of all the observed sequences to learn the model. So just say in the neural network version of language models, let's call the model parameters theta. Then we're going to maximize the log likelihood of X given with respect to theta, and so log likelihood of a sequence of t is equivalent to the summation of each token, the log likelihood of each token given its context to the left. That's the standard language models. And in the neural network version, there's a conditional probability. The conditional part, the context to the left, is typically presented using some latent vectors called H. And so in this graph shows the standard recurrent neural network architecture. So they learn some linear transformation matrices given the input and another input from previous step of the hidden vectors, and you map that to the next hidden vector. So like this. You can see that the original objective function, the context to the left, is represented as H0 in the first step, and H1 in the second step, and so on. Then so one limitation of this kind of language models, although it's natural for simultaneous speech recognition, but for many other important applications like machine translation or some other text summarization, text categorization, question answering, you actually have a simultaneous access of all the input. But this model just allow you to leverage this context from left to right. So that does not, so in that sense, in order to predict this language, the next token, they only use the past information, but not the future information. So in other words, they cannot leverage a bidirectional context. That's a clearly limitation. Then how to address that limitation? Then people actually, in the past few years, and doing that is called bidirectional language modeling, from left to right and right to left. So they essentially they use the actually same kind of architecture, RNN, but you just make that forward and backward, 2 ways. And ElMo, in fact, have this exactly use this kind of architecture. So here's the high-level graphical representation of the ElMo's architecture. The yellow part is the input layer, whereas that each yellow box represent the encoding of each token in the input sequence, not without context. And then this token will simultaneously send into the system and produce the output as the green layers, so that also these green layers are latent variables, latent vectors, and the subscript from 1 to n again. So each one is the token representation conditioned on its context. And the conditions are estimated, our conditional presentation are produced by two component system. The 2 boxes in the middle, on the left is the left to right language models in the multi-layer, and on the right middle on the right is the right to left language models. And those 2 boxes are optimized independently. So then only at the last layer, they produce a latent representation are concatenated as the final representation learned by ElMo. And the multi-layers just try to make this, because there's all their RNNs are nonlinear models, so they basically make these latent features are the more and more complicated or enriched with in the enriched scope of the context. So these are just some detailed notion of this objective function and how this contexts are this conditional probability are estimated. Essentially, you can see this again. This is softmax function, and they have 2 components. One is the encoding of each token out of context, and the context latent encoding of the context to the left. That's part of the left to right language models. And symmetrically, you can also estimate the probability from right to left. Everything is the same except the arrows, the direction are different. So you can see that here is a token context to the right, and the token here, current token here. So, and that's the multi-layer notion that, which I already said that at the last layer, and they separately learned left to right latent hidden vectors, and right to left hidden vectors are jointly are concatenated as the final output. And typically that the pre-training of ElMo gives you multi-layer representation of this of those latent vectors. And in the downstream tasks, when you do the fine-tuning, and those multi-layer latent vectors are combined linearly and with some weights, and the weights can be learned from the downstream tasks based on the task-specific data. So to summarize, what is the pros of the ElMo or similar methods? Because they do this autoregressive factorization of their to characterize the objective function, so which is natural and simple and principled. The cons is that they have two part of the parameters. One part is for left-right language models. Another part is for right-left, and these two parts does not communicate each other, and they're not jointly optimized. When humans make a prediction, if they're given the input sequence, they want to estimate, they want to consider the meaning of each word. Human will naturally think about the context of left and context of right. They will not treat them as independent. But this model, in fact, does not have the ability to do that. So that's clearly suboptimal. Now let's enter the BERT as a representative example of autoencoding methods. That's, by the way, is the 2019 best paper in NACO. So now we can put ElMo and BERT side by side. Let's see the difference. Again, the yellow part layer is the input layer. The green layer is the output layer. And you can see in the middle, BERT does have unified framework, does not have two separate building blocks. So that means by this architecture, you can see that the learning, the latent representation, that means the output of any middle layer nodes, is dependent on the previous layer's input on both left and right, so that BERT's architecture naturally leverage both left and right contextual information simultaneously in the unified framework. So they don't have this separate two sub modules as ElMo. And then the question is how come how BERT doing its training, because both are essentially all these methods really is needed to solve the first fundamental problem. So how do you come out with the training pairs, the input-output pairs? And the autoregressive model, the pairs is each token and its left context. That's the training pairs. But in BERT, then how do you use unsupervised data to come out with the pairs? So that is the difference is the BERT uses something called masked language modeling. Is a unique way, differently from an autoregressive model, to come to the training pairs. Other part is already said that it does not separate sub modules to optimize independently. And another important part is the building blocks in BERT is not a RNN or LSTM, but is a transformer, which also give the BERT some kind of advantages. So we're going to see all those major differences for BERT in comparison with ElMo, or you can say autoregressive methods in comparison versus autoregressive, autoregressive methods, autoencoding versus autoregression. So this is on left part, subgraph A is a typical architecture for RNN. So that means here's the input sequence tokens, x of 1, x of 2, up to x of n. And the hidden layers is also like that. So that means the dependency, if say is the position latent variable H5, that the dependency of that to the early token X1, there's a long chain here. And in a transformer, this is typical architecture of transformer or attention-based mechanism. So that means each latent variables is directly connected to all the input variables at any latent layer. So in that sense, the longest chain from any variable to a previous layer input is maximum length is 1. So here is maximum length is the sequence length. The sequence length can be 500. That's very long. There is a well-known problem in neural network training. It's called it's called the gradient vanishing problem. So basically, you have the nonlinear gate and you have a long chain of dependencies, and then you typically the model is very difficult to optimize due to this kind of problem. But transformer have this kind of simple direct connections, then they would avoid this kind of problem. And practically, transformer, since it's developed and shows a better performance than this RNNs or RNN-based models when you have larger amount of training data or unsupervised data. So that is an advantage, as the building blocks have a better modules in in BERT or AE models. And here is the difference in the how do we come out and pair the training data. So this slide shows that, as I said, these autoregressive models, you can say that all the training data, original supervised data, is decoupled into this token, every token, and is a context to the left. Those kind of training pairs. Or if they added bidirectional language model, you have another pair, each token and the context to the right. So that you have two pairs. That's the way you produce the training pairs. But in masked language modeling, that's the BERT is based on, what they do is they do not distinguish left, they basically want to leverage. In order to predict any token, the first thing is given the input token, they choose some portion of the input token and just replace that, they call the mask. They use some mask operation, just replace a subset of token by mask, and then they use this mask token as the output. And so this is then the remaining of the tokens sequence as the input. So then they came out with the input-output pairs. And further, they mask the part, the output tokens, they further introduce, here's a notation, the remaining, the original sequence with the mask symbols together is called corrupted sequence or input sequence, denoted by X hat. Originally just X, and they replace the subset by masks, and they come out the sequence called corrupted sequence X hat. And the being masked part is called X bar. That's another subsequence. And they further decompose the subsequence of the X bar into individual token in that X bar, and just assuming there's a conditional probability given X hat of these two mask tokens are independent. That is the way that masked language model produce the unsupervised training pairs. So then that's some inherited weakness of this kind of treatment, because first of all, they introduced the mask symbol into the input, and the mask symbol is not the original part of your observed data, and it's only used as in your training sequence, but it never occurs. The mask symbols are never occurred in the test data. So in that sense, it's create a training set and test set discrepancy. So and another thing is the independence assumption between the output tokens. So that is the problem, the limitation or shortcomings of BERT. So this part I already said that. So basically, to be put what I said into be precise, the objective function is to try to maximize for any sequence in your data collection. You produce the X bar, X hat pairs, and you maximize this probability of that. And when you, so that those probability is estimated through multi-parameter theta. So essentially you end up with predicting this kind of conditional probability of each token given X hat. And we say that they have two limitations. Yeah, I already said that is both the context corruption part and the independence assumption part. So this slide shows the published performance of BERT compared to the state-of-the-art for methods of ELMOs and GPT models. So it's just 1 year apart, but it's in fact the last 2 or 3 years there's a dramatic improvement in neural network on many natural language text and information retrieval, text classification, question answering, and so on. So those are benchmark data sets. Some are NLP tasks, some are information extraction or QA tasks. And so the bar on the leftmost, this group, is the average of the bar across different data sets. So if you want a short take-home message, you can just look at this set of the bars. And the pink bar is state-of-the-art method, best results so far before GPT was developed. And GPT and ELMo are really published in the same year, so you can consider them the same time, or that the yellow bar is a stronger version of ELMo, so ELMo plus attention. So that's the better version of the original ELMo. And the green bar is the OpenAI GPT. So the GPT is slightly better than the best results at the time, also outperform ELMo. And BERT is the dark blue bar. So BERT at the time was the state of art. So I already said that the pros is they have very strong performance at the time and in many tasks. And the cons is the independence assumption is not justified. Context corruption is suboptimal. So now, how do we overcome those limitations? That's the key idea in XLNet, which actually published in NIPS 2019. The high-level similarity is similar to BERT. It's also left-to-right leverage left-to-right context in a unified framework. and it's built on top of transformer as a building blocks, or actually it's built on top of transformer XL, is an improved version, a more scalable version than transformer. And the main difference is use permutation language modeling to avoid the context corruption problem in BERT. It also uses autoregressive factorization to leverage the full context to avoid the independence assumption that about output variables in BERT. So the last one is even a better transformer building blocks. So then let's start from their objective function, and in order to introduce a key idea in XLNet. The first line, which is copied from previous slides, BERT is optimizing this guy. And XLNet, that we introduce some new concepts or new notations. First of all, Z sub n, for each observed training sequence, just say, let's think about that as the X. That we Z sub n is all the possible permutation of length n input tokens in X. So that is then lowercase z is one element in that Z sub n set. So for example, if I have a sequence of 4, a length of 4, then we could have Z is the factorization order. So we can treat that this input sequence originally is 1, 2, 3, 4. Then we can permute the order to 3, 2, 4, 1 or any others. So you can see that 4 factorial possible permutations, the permutation orders. Then X tilde sub Z is a given order of Z was the sequence you end up with. Okay, so that's just notation. Then, so what we're really optimizing here, we're optimizing that, of course, this object is just written as a single X, but you can easily extend that to all the training sequences for many X sub I. And we just write the single sequence version of the objective function. So we actually maximize the expectation of the log likelihood of all the permutation X tilde. And the X tilde part inside permutation, it's this X tilde is further factorized here. Each token in X tilde, we actually do this autoregressive way of factorization. That means each token given its context to the left. This is just an objective function. Then we're going to have a few more slides to dive into the intuition. So the intuition is like this. Given any sequence X, then how can we possibly factorize the probability of PX using Markov chain? You can do that from 1 to 3, 4 in the order. You can change any other order. They are all equivalent. They should, if those all the conditional probabilities are accurately, precisely estimated, or they are true probabilities, and all this factorization should have an equal value of PX. So that just is from just the factorization standard, the joint probability of any sequence can factorize in n factorial different ways. So this is actually very interesting. So that means for each input sequence, you can get an n factorial number of pairs, because in this factorization, you only need this subset of model parameters in compute that. And this factorization, this set, you use a different set of model parameters, estimate that, and they all should be equal. I think so. Then so in this also we can see that this kind of factorization, that if each one utilize only the left to right context, but altogether, then they make the prediction of each token depend on both left and right context. We can see that in here. In this factorization, supposedly we focus on the latent representation of x2 given x2, but then you can see in his when we try to produce that latent representation, in this factorization we use this depend on x1. In this factorization depend on x4. So, but if you optimize the probability over expectation of all these different factorizations, then you actually, for each token, you're actually leveraging the context both in the left and the right. So to be more, make that more concrete, supposedly we have the factorization of 1, 2, 3, 4. So now you can see that shows the input x 1, 2, 3, 4, and the output is the context-based presentation. So basically, say x1. So here this is x2 is depend on only x1. There's s3 depend on x2, x3, and so on. That's the dependency from left to right. Then you do another factorization. So you focus on, then in this factorization, let's think about x3. x3 depend on both x1 and x2. And x2 depend on x1, x3, x4. So essentially, it's jointly, it's not only dependent on the left or right. So now put them together in different factorizations. Supposedly, one want to predict x3. So in one factorization, that x3 is come to the first. So it does not depend on any other. Another factorization and depend on that x3 depend on x2 and x4. Yet another factorization is dependent on x1, x2, x4, and so on. So if we put it together, essentially for each kind of training pair of the permutated sequence and the optimal token, you learn part of your neural network connections. And but for different pairs, you train a different part of your neural network. But altogether, you type them together. All the permutations you can generate, you try to learn that their probability scores should be, the expectation should be maximized. So more details, I will skip that. There's some implementation details. That means you need to be clever. How do you do this during the training process? How do you reconstruct the connection given any permutation? And how do you encode the internal latent representation of each position? So I'll skip these details. So here's the main results. In previous slides, we showed that BERT actually outperform most of other methods. And here we only show how XLNet perform in comparison with BERT. On the left corner, on the left subgraph compares BERT and XLNet on some QA tasks, different QA task data collections, that the orange bar is the XLNet and the blue bar is the BERT, so that XLNet uniformly outperform BERT. And on the subgraph B is some other classification tasks or regression tasks. Again, XLNet outperform BERT uniformly. So essentially, the empirical results support the claimed advantages about XLNet. So the take-home message here is put everything together. We just say, I want to say that unsupervised representation learning has made a significant impact on machine learning and the downstream tasks. And we showed you 3 representative examples and to characterize the trend in the development of those methods. Of course, there's more work to be done for further scale up, so we can leverage even larger data collections or longer talk context, and also to apply many important and challenging application areas, such as time series anomaly detection, graph-based learning, and so on. So it reference 2 parts for word embedding and for later effort. So that's pretty much what I have to cover. Any questions?
Okay, thank you, Yiming.